Okay, the Matrix, it's a movie, and it's also a math concept. Basically, you're going to learn how to take these things that look like this and learn how to multiply them, add them, subtract them. You know, you have a whole unit on this, so you're going to be pretty good at taking these just sets of numbers and doing things with them. And it's pretty easy. It really is. It's kind of, you know, pretty self-explanatory. Today we're going to basically make sure you get the terminology, and we're going to do a little bit with graphing, adding, subtracting, which is super easy, and scalar multiplying, which is also super easy. So this is a pretty easy day. The main idea is it's a rectangular arrangement of numbers. And these are each called an element. I've also heard them called other things, but we're going to call them an element of the matrix. And they're obviously in rows and columns, and it's one of the most important things that you need to understand is which one's which. A column, I like to think of it this way because you never see columns going sideways. Okay, otherwise it wouldn't be a column. Okay, columns go up and down, and so you have to know in this thing, if I say column 1, can you lock in on where column 1 is? Column 1's right there. Okay, and if you were thinking of something else, you got to get that straight. The columns are up and down. Rows are kind of like in a baseball field. And so the rows, I have this little link here to target field to just kind of remind you. See if I can. Computer's working really hard because this is a like a 3D simulation thing. So here's target field. Anybody that actually there last night at the opener? Nobody. Boo. Okay. Anyway, and if you were at, you wanted to buy a extra value seat in this area, it looks like it would cost you 28 bucks. Anyway, you click in this, and then it loads up what your view would be like from that seat. Makes it look like it's a pretty good seat for 28 bucks. Anyway, and of course, the reason I'm doing this is just to talk about rows. The rows in here are going this way. They're going across. I can't draw on it because, oh, there we go. The rows go across like that. Okay? All you really have to remember is that columns go up and down, and then you'll obviously know that the rows go the other way. All right. Now, one other thing, one last thought on the rows and columns. Rows are always done first and columns always second, so it's always R then C. You got to keep that in your head. With matrices, that's the number one mistake, is to do it backwards. Rows always come first, columns always come next. Rows then columns, kind of like RC Cola or remote control. Okay. So basically, this is a what by what matrix. We could call it a 3 by 2, or you could call it a 2 by 3, and that's exactly why I was saying you got to keep that straight. It's got to be rows, then columns. So how many rows does this thing have? 2. How many columns does it have? 3. So it's a 2 by 3 matrix. Okay? So what's this one? How many rows does it have? 4 rows. 1, 2, 3, 4. How many columns does it have? So it's a 4 by 3 matrix because it's got 3 columns. 1, 2, 3. Okay? All right, I don't think you need any more on that. That's all there is to that. That's super simple. If it has the same number, it's called a square matrix. Does it make sense? If it's a 3 by 3, then it's got the same both ways, kind of like a square is the same both ways, you know, same on both sides, length and width. All right. And basically, here's some situations where you actually, you know, see these. A seating chart is just a matrix. It's a matrix that you put people into, okay? Your monthly schedule, if you look at, you know, January and you look at all of the rows and columns, the rows or the columns are like days of the week, like Tuesday, Wednesday, Thursday. So there's a lot of things in your real life that are matrix, or in a matrix form. So notation. So A, I, J, where I is the row and J is the column. So if they said A1, 2, that means always, remember, rows then columns. See why you can get messed up if you start doing columns and rows? Because it's 1, 2. That must be row 1 and column 2. Row 1, column 2. And that must be the 3 then. Does that make sense? So if I said, where is A 4, comma 1, I hope you would say it's row 4, column 1, and there isn't a row 4, so that doesn't exist in this matrix. All right, so if you understood that, then tell me what's that one right there. It's A something something. It's A, and then you'd go, what row is it in, Mr. N? Okay. Comma. What column is it in? That's A 1, comma 3 then. Raise your hand if you had that right. Okay, good. Moving on. Matrices were initially based on systems of linear equations. Do you get that all these numbers have been plucked out? That was a -1. And then put over here. Those 4 spots go here, and here, here, and there. And the cool part is that if you have a system, really complicated system like this, if you had to solve it algebraically, it's got 3 variables, it would take you a long time to solve it algebraically. If you just make it into a matrix like this, you can use your calculator to solve that system of equations and tell you, oh, x must be this, y must be this, and z must be that. It's really, really powerful. Like, if you had this on the ACT, it would be considered one of the hardest questions. It would take you a long time to solve algebraically. But once we teach you how to put it into a matrix, you just have to do reduced row echelon form, RREF. You have no idea what that means, I know. But you would do that RREF button on the matrix, and boom, it's going to tell you the answer for x and y and z. And so anyway, this is an example of how we'd use matrices to solve cool problems. All right, so another one would be, if you wanted to make geometry into matrices, you just have to use these as the points. That's like 1, comma 2. That's like -2, comma 1. You know, they're dots on the graph. So basically, if you list the dots and then you assume you connect them, but here's the only problem. You have to kind of make some assumptions, like, couldn't I have connected these in a different way? Wouldn't I had to go around the outside like that, would I? So it's a little bit of a stretch to make this into geometry, because there's multiple ways you could have connected these. I could have connected it that, and then that, and then that, and then that. I mean, there's a lot of ways you could connect the dots. But at least these are just the points. That's pretty simple. And that means that they have to be divided into x's and y's. And obviously, it can't be like, these are the x's, and these are all the y's. Duh, it can't be divided up that way. And then logically, if that's got to be x's and that's got to be y's, you know, like one or the other, which one do you think the top row is? X's. Because x's are always given first in the xy coordinate. So the very first one we come to is our x, and then the rest of them must be x's. So these are all x's, the x part of the points, and these are the other parts of the y parts of the points. All right, moving on. Adding matrices, super simple. You just have to have corresponding. Do you remember that word from geometry? Corresponding angles, or the angles that are kind of like each other. You know, when you had corresponding angles, you would say that this angle right here, angle, let's say x, corresponds with angle y. They're kind of like each other relative to each other. They're both the upper left-hand corner angle out of these 4, you know. So anyway, that's corresponding. Well, I'm using that same word here. Corresponding with this one is that one. Doesn't that make sense to you? They kind of go together, and so when you actually add them together, what do you get? 7. Is that the final answer to this question? No, that's the first part to the question. And then corresponding with the 2, I have an 8, and so what do? I will make 10. And then corresponding with the 7, I have a 10, and that makes 17. So my answer is 7, 10, 17. That's all there is to it. Now, This one also, these correspond. That corresponds with that, and I'm just subtracting, so 1 minus 3 is going to be -2, and you have to make a big answer bank, and I don't think we need to... Once you get that concept, it's pretty easy. This last one, what's weird about it? There's only one row in that one. That means you simply cannot do it. If they don't match up, this one doesn't have a corresponding number over here. You could say it's this one, but then you have to like try to put this one and this one with the same number, and all kinds of things start not making sense. And then how kind of an answer are you going to put? You're going to put an answer with one row or two rows. And anyway, so these, if they're not the same size, you just can't do them, and you have no solution. Here's the fastest way to write no solution. It's called the empty set. The 0 with a slash through it means the set of solutions to this is empty, meaning there is no solution. Okay, anyway, scalar multiplication, that is where you're scaling it up. Take a wild guess how many times bigger I'm trying to make that matrix. 3 times bigger, that's a scale factor. That's called scaling and scalar multiplication. So do you get I'm just going to multiply everything by 3? That's it. So 3 times 7 is 21. Would you please finish it? And I'd like you to compare it with the person sitting across from you. It's going to be these 2 rows. And these 2 rows, you're going to have to go kind of diagonal back, diagonal back, diagonal back, and then it gets close. You last 3 people, I'll compare. And then you guys across from each other and you 3 people back there. Compare your answer for this scalar multiplication. I'll pause for a second while you do that. Okay, so here's what you should have had. 7 times 3 makes 21. 3 times 2 makes 6. 3 times the 0 makes 0. And 3 times -4 makes -12. Use 4 different colors. There we go. My matrix was a what by what matrix? 2 by 2. Tell me which one this was. A, 2, 1. That'll test whether or not you know that notation yet. What was the answer for A sub 2, 1? Yes, ma'am? And tell me how you knew that, because it's what? Yes, row and then column. So row 2, would you all agree that that's row 2? And then column 1, and where do they overlap? The 6. So it's the 6. Good job. Okay. Really on this, it's just combining this with adding. So you'd find this answer, and you'd find that answer, and then you'd put the answer in the corresponding spot. So, for instance, -1.5 times 1. That makes -1.5. Plus the 4 times the 0, which makes 0. What's the answer? -1.5. All right, I'd like you to finish that one. They'll test your mental math abilities too. Can you do 1.5 times 6 in your head? Do the 1 times the 6, then do half of 6. It's not that bad. Okay? Figure out the rest of that matrix answer. I'll pause while you try that. Okay, and basically that's all I have for you on matrices for today. We've got these triangles graphed at the end. I think I may not have had that on the video, but it's really not super important or complicated. Your assignment for today is day 1 of matrices.